All righty, folks. So good to see you guys today. So good to see you. So today we're going to be talking a little bit more about sums in general. So some Riemann sums, but just in general, just a wide variety of sums. So we've talked about how sums can be some sort of we can deal with them with Riemann sums, but how we can use a table then to kind of help us out here. So say I give you a function like this. And this graph, these are just selected values of f of x. So, I mean, there's nothing special really about them, just selected values. And say I ask you guys to determine what function this is. Now, again, I put little dash lines, but realize this function could be like, it could go up and down and up and down. A lot of things could happen here. We don't really know what this f of x looks like. We just have these selected values on our function. All right. So what we're going to start off with today is we're going to look at just some different types of sums. A couple we've already dealt with before, a few that we haven't. So we're going to look at something called a left sum, which we've dealt with. And we're going to look at a right sum. And again, we've looked at that one already as well. And then the last one we're going to look at is or for right now, is a trapezoidal sum. Oh, these are going to be the things that we kind of play with for right now. So I got this selected value, and we've already kind of talked about this. Notice this first function, if I'm looking at it here, this first function, if it's the left sum, that means I'm taking between these first two values here. Oh, let's pick a different value here. Let's make it orange. So notice this interval right here is going to give me the interval between these first two. So if I'm taking the left sum, that means I'm going from the left side up here to my y value. So the rectangle would look like this. And if I was doing the left sum, I'd be going up to the rectangle and over to the end of the width. If I was taking the right sum, then I'd start at the right hand value of this and go over this way. And that'd be my right hand sum. The height would be based on the right point. So when we're talking about sums, that's really what we're talking about here. So we have all these different intervals we're playing with here. Let's put the intervals out here so we at least can see them. There's an interval here. That's going to help us kind of see the left and the right midpoint values. We got one right here. It's also going to help us see just essentially the base value as well. Not midpoint values, I'm sorry, x values. All right, so that way now hopefully we'll be able to pick up where all these values are. And if you notice, based upon all these bases here, that tells me that I'm going to have 6 different rectangles. And remember, a rectangle, the name for rectangle is really the same thing as partition. Okay, so rectangle, when we're saying rectangles, that's the same thing as partition. That's the fancy schmancy way to call it. But all we're really looking for is the area of rectangles. So if I'm looking at the left sum, that means I'm going to be starting all my values on the left-hand side to build my rectangle. So let's see my first one. So there's a rectangle. Start on the left-hand side here. There's a rectangle. Start on the left-hand side. And there's my rectangle. Start on the left-hand side. And you can kind of see how we create all these areas to be able to approximate the value of this area of our sums. Let's see here. And so we create essentially all these different rectangles to help us see all what this area could possibly be. So this right here, this is our left sum. And we also said that the area between these, notice this base, the width between is always however long this is, 2, 1, that's 3. We can start to see the base of these rectangles. So that's 2, and this would be 3 and 1. Now last class, when we were in class, we talked about how those rectangles are really nothing more than just the difference between these x values. So we don't actually have to have this drawn out because we can already see what the x values are. You can see in between these x values, we get the width of our rectangles. Now, when I go up here, I see this 1, 2, 3. So that has a height of 3. This has a height of 4. This has a height of 5. This has a height of 9 on this rectangle. This rectangle right here has a height of 8. And this rectangle right here has a height of, did I do that one wrong? Oh, height of 6. No, we're good. And what we said before is we really didn't actually need to ever have those heights, again, drawn in the shape, because if I were to follow my left shape down here, notice, when I go down the left-hand leg of this, 3, well, that was the height right here. We go down this left-hand side right here, 4, notice, that's the height right here. And we keep doing this. If you notice, we keep doing this. The left sum is always going to be the y value that comes on the left-hand side of those arrows. And so when we're dealing with our sums, it's always the y value, the y value, the y value. So if I wanted to know what my left sum actually was, then I would basically say, all right, it's going to be approximate. Now we always use an approximate for a sum because these are not exact areas. So my first rectangle was 2 by 3, or it was 2 times 3. So 2 times 3 plus 1 times 4 plus 3 times 5 plus 2 times 9 plus 3 times 8 plus 1 times 6. And we can get that approximate value for what that area might actually be. So if I put it in my calculator here, now on the AP test, we don't ever simplify anything. We'll just leave these alone. We won't actually ever add these. The only time you ever have to add them is if you're going to end up having to use it for an answer later on. But in this case, I wouldn't have to. I'm just finding the left sum. And that would be 73. I'm finding the left sum, or the left Riemann sum. So if that's the left sum, then the right sum is going to be using the right values. So if I come back here and I take a look at the right sum, well, that would be using the right endpoint value. Notice it skips over here and it's going to be making this rectangle. The right Riemann sum is going to give us a value that looks like this. Is it a little closer? Maybe. It's not always going to be closer. If it is, it's kind of hit and miss. It all depends on, honestly, we'll see this later, it all depends on the concavity of the shape. But I can come up with the right Riemann sum. And actually, I meant to make those purple. Oh, that's okay. So we'll make it purple notch. Make that green. Does that work? Nope. Will not work. When in doubt, can always switch. All right, so we have our right Riemann sum. So notice on the right Riemann sum, this height right here was 4, and then it was 5, and then it was 9, 8, 6, 8. Well, if I look at my little carrots up here in a way, I can see that when I had a width of 2, the right Riemann sum was the y value on the right-hand side. It was the y value on the right-hand side, y value on the right-hand side. You can see how all these kind of pair up to allow us to figure out what those areas would actually be. So if I wanted to know what that actual approximate is, I would say, all right, well, it's approximately, and I would write my area like this, 2 times 4 plus 1 times 5 plus 3 times 9 plus 2 times 8 plus 3 times 6 plus 1 times 8, which would give us the following value: 8 plus 5 plus 27 plus 16 plus 18 plus 8, and that would be 82. And the left Riemann sum and the right Riemann sums, we've already pretty much looked at those already. Now, what if we did something called a trapezoidal sum? Now, there's a rule called a trapezoidal rule, and that only exists if all these partitions, all these rectangles have the same width. If all the rectangles have the same width, we say then that it is normed width, okay? Normed width. Norm width. That means all rectangles, partitions, have the same width. And when you're actually dealing with that, when you want to find that norm width, we've actually been doing it already. The norm width comes from that idea of delta x. Oopsies, not the color we wanted. We wanted red here. Go on this side too. Delta x. That's a hard triangle to draw. Delta x equals b minus a over n. So that's what we mean by normed width. That makes every rectangle the same width. In this case, it would be 13 minus 1 divided by 6, because I have 6 rectangles. 13 is my largest x value, 1 is my smallest x value, and I divide by 6 because I had 6 rectangles. But that's not what we have here. But what mathematicians found out is they said, wait a second. It's all right for us to use rectangles, but another geometric shape that might be a little bit closer would be a trapezoid. Notice a trapezoid takes 2 things. And when that happens, notice what's going on here now. On a trapezoidal sum, our partition width is no longer the base. It became the height of the trapezoid, because the trapezoid, the height is always perpendicular to the 2 bases. So that means this 2 now is no longer the base, it just became the height. So the width here is 2 or 3 for this base, and this base over here is 4. So notice what a trapezoid does. It uses both of these. So this particular 2, it had one base that's 3, and it had one base that's 4, as 2 was the new height. Likewise, we're going to find that 1 will have one base of 4 and one at 5. 3 is going to have a base of 5 and a base of 9. 2 will have a base of 9. And you can see now trapezoids are going to end up use both of those actual bases. But notice what the trapezoidal area looks like. And again, it's going to follow along this line here. But imagine there was an actual curve. It wouldn't be following exactly the curve in general. Now I can show you what I mean by that. Again, if say this graph looked like this. Notice the trapezoid doesn't amazingly get it perfect, but it gets it pretty darn close. Gets it a lot closer than the other ones did. So that trapezoidal sum, it's an even closer sum. And if we do that one, we're going to be using the area of a trapezoid. Now, just in case anybody here forgot what the area of a trapezoid is, it's the height times base 1 plus base 2. Every year, I always get at least one or two people in calculus that forgot the area of a trapezoid, which is fine. I get that you guys haven't done it in a couple of years. And if it's not something you've done yet and you haven't done your SATs yet, yeah, you may not necessarily remember it. That's okay. So our height is 2 times base 1 plus base 2 divided by 2. There's our first trapezoid. So plus our height of 1 times 4 plus 5 divided by 2 plus 3 times 5 plus 9 plus 2 times 9 plus 8. So this is a trapezoidal sum. Plus 3 times 8 plus 6 plus 1 times 6 plus 8. Notice, you can see, and this is, if we were to look at the trapezoidal rule, we'd see this a little bit more. You'd notice that each of these bases were used twice. All the inside bases were used 2 times. The outside base, those were only used 1 time. So these were all used 2 times. All these y values were used 2 times on a trapezoidal sum. Where these outer bases, they were only used 1 time. All right, so when we plug this into our calculator, friends, why don't you go ahead and take a second here and do that. I haven't actually done it either, so I need to do that as well. Plus 4.5 plus, what is that going to be? 14, 7.1 plus 17 plus 21 plus 7. And I ended up getting 77.5. And if you notice, that falls between my left sum and my right sum. Now, sometimes my left sum might be greater than it, my right sum lower than it, but it does fall between. What's the difference, you think, between the left sum and the trapezoidal? So what if we were to take those differences? The trapezoidal sum minus the left sum. What would that be? 77.5 minus 73. Oh, I did equal 73, though. Well, that's not mathematically true. No, so it's about 4.5 away. My trapezoidal sum is about 4.5 away from my left sum. How far is it away from my right sum? Let's take the right sum and then subtract the trapezoidal sum from it. How far away is it from that? 82 minus 77.5 equals 4.5. If you notice, the trapezoidal sum is the same distance from the left sum as it is from the right sum. And in fact, it's always going to be. It's always going to be, because if you think about it, the left sum uses the left numbers. They use the left y values, so 1, 2, 3, 4, 5, and 6. The right sum used the right y values, 1, 2, 3, 4, 5, and 6. Notice, if we were to add them together, the left sum and the right sum, they would have used the exact same y values the same amount of times as the trapezoidal. Turns out the trapezoidal sum really is just the average of the left sum and the right sum. So that's actually another way to figure it out. The trapezoidal sum equals the left sum plus the right sum divided by 2. Now, I wouldn't necessarily always figure it out that way, because I mean, what if you're only doing a trapezoidal sum? I mean, if you're only doing the trapezoidal sum, I wouldn't necessarily go through and figure out the left sum and the right sum just because. But it is true that the trapezoidal sum is going to be the average of the two. That's why it makes it more, it's a more realistic sum. It's a better approximate than the left sum and the right sum, majority of the time. Not always, but majority of the time. So what we're going to do today is we're going to play around with these sums just a little bit here. All right. So we don't need the graph paper anymore, because we're not going to graph the dots. So as long as we have the table, we're good to go. So let's go and give ourselves a new window. Let's give ourselves a clear window here. There we are. So we need a table here. Say I give you some value of x. I'll give you a table of all my x's and y's. Let's see, I'll make this 2, we'll make this 4, and we'll make that 5. We're just going to create a table of values. Just make sure we have it here. 7, 6, 9, and 11. Let's make that black just for the fun of it. All right, so I'm giving you a table of values here. And again, we don't necessarily need a graph. As long as we have a table of values, we can at least approximate what the values might look like. All right. And what I want you guys to do is I want you to figure out the left sum, the right sum, and the trapezoidal sum. The left sum, the right sum, and the trapezoidal sum. Why don't you guys go ahead and pause the video. And when you do the trapezoidal sum, I want you to actually, if you are going to go left sum divided plus right sum divided by 2, that's fine, but I still want you to write out the values. You need to be able to see that. So go ahead and pause the video and do it real quickly yourself, and we'll come back and take a look at it. All right, let's see how you did here, friends. So the width, or the base, is always going to be the difference in the x value. So I have a base of 2, base of 1, base of 3. Oh, what's that? A base of 1, a base of 3, or these are also the heights of the trapezoids, and 2. So when I'm dealing with my left sum, and when I'm dealing with my left sum here, I'm going to be taking all the left values down here. All the left values. By the way, how many partitions do we have? Can you tell? 1, 2, 3, 4, 5, 6, 7. There's 7 partitions. Okay. So left sum, 2 times 2, plus 1 times 4, plus 3 times 5, plus 1 times 4, plus 3 times 7 plus 1 times 6 plus 2 times 9. And plug it in your calculator and get yourself a value. The right sum, you just go down the right tail. So the right sum, and again, if we're on the AP test on the free response, we're not actually going to total these up here. So we have 2 times 4 plus 1 times 5 plus 3 times 4 plus 1 times 7 plus 3 times 6, 1 times 9, and 2 times 11. Plug that in your graphing calculator, and you got yourself an answer. The trapezoidal sum, here we go. The red bases just became red heights now. They're the height. And we take both tails. So 2 times 2 plus 4 over 2. Plus 1 times 4 plus 5 over 2. Plus 3 times 5 plus 4. All over 2. And 1 times 4 plus 7. And 7 and 6. And 6 and 9. And 9 and 11. So we got the left sum, the right sum, and the trapezoidal sum. Now, notice there's one other sum we could possibly do, but we can't do it on here. So I'm going to go ahead and get rid of this. I'm going to put another table up, and we'll see if we can actually talk briefly about it. So let's see if we can do that here real quick. Let's see here. I need to get some numbers up here. Let's try x 0, 4, 8, 12, 16, 20, 24, 2, 7, 6, 4. Let's go 7. How about 10? And 11. There we go. That'll work for us there. Get ourselves, finish this table off here. Actually, I think before I actually go over that last other type of sum, I think I'm going to have you guys go ahead and do your left sum, right sum, and trapezoidal sum again here. Let's make sure we fully have this here. Left sum, right sum, and trapezoidal sum. All right, friends, why don't you guys go ahead and try this one real quickly. Go and pause the video and get it done. All right. All right, here you go. So you guys are probably all saw it. You're like, they're all 4, man. So they're all 4. They're all 4. All the widths are 4. That means they are normed width. They're all normed width. So then the left sum then, it's not too hard to come up with. We take all the left values, we have 4 times 2. And I made a big boo-boo, friends. I put equals. That needs to be an approximate. These are all approximates. 4 times 2. 4 times 7. 4 times 6. 4 times 4. 4 times 7. And 4 times 10. There's our left sum, right sum. Same exact values we had before. It's just instead of 4 times 2, we'll have a 4 times 11 on this thing. And you guys, again, you did on the free response portion, you leave it like this. If it's multiple choice, you'll have to plug it in your calculator or just add it up real quick and figure out what the actual value is. And trapezoidal, again, it's the left sum plus the right sum divided by 2, but let's make sure we also understand how that works too. Plus 7. And you guys will get a sum somewhere on your test, multiple choice free response. Almost always you'll have at least this be part of one of your free response questions. So all right, so we have these different left sum, the right sum. We have these different sums available to us. But if we go back to the definition of what the Riemann sum actually said. So you don't have to sit there and thumb through your notes from yesterday. Here's what it said. N I equals 1. So we have an index here. And notice, norm, they're talking about the width, the norm width. And again, a sum doesn't have to be normed width. Although it is for a Riemann sum, that is. And x is between x sub I minus 1. Your C is usually one of these things. And we said that when we're dealing with this, friends, that x of I minus 1, well, that would have been that was the x value we would have used for the left sum if we were to actually use the technical formula to figure it out, which we're not going to do here. And this one right here, this would have been the right sum. But realize it could be anything. It could be anything in between the left sum and the right sum. Like, for instance, one of the things that we use a lot is something called a midpoint sum. In other words, the number that's halfway between those. Now, if you notice our table above here, so I'm not saying that C sub I is the midpoint. I'm saying it definitely could be. So the middle between the two x values could be. The middle between the left and the right endpoint could be. But in order to create a midpoint, first of all, we have to have a middle. And if you notice on these, when our width was 4, I don't have a middle. In order to create a middle, whoopsies, don't want to do that. Kind of need those values. Let's do this real quick. In order to create a middle, I have to move and not use every single partition. I can only use certain partitions. So for instance, if I wanted to create a middle, a midpoint, I'd have to, maybe I don't go right from 0 to 4. Maybe I go 0 to 8. Now, realize just because I'm skipping a partition doesn't mean that the number is in the midpoint. In order to have a midpoint sum, a couple things have to exist. First of all, I have to have normed width partitions. Everything's got to be normed width. If it's not normed width, friends, I can't do this. So they all got to be normed width. In this case, all of these widths were 4. The second thing that has to be true, if I can only use an even number of partitions to do a midpoint. And if you think about it, that kind of makes sense because the midpoint is going to be in the middle of 2 things. So everything has to come in pairs. If I have 7 partitions like we had on the second one, I wouldn't have been able to use every partition to do a midpoint sum. I could only do a midpoint sum of part of the terms. So we have to have they have to be normed width, and we have to have an even number of partitions. So if I want to do a midpoint sum partition, I want to do a midpoint sum, I have to skip. I need to have all of them be the same. So watch, I'm going to skip 12 and go to 16. That gave me a width of 8. So from 16, I'm going to skip 20 and go to 24. So I'm only going to be using quote unquote 3 partitions. Okay. Now realize the left sum is still going down the left side of these partitions. We don't want a left sum. The right sum is still going down the right side of these partitions. We don't want the right sum. We want the midpoint sum. That's essentially the sum that is in the middle. So if I'm doing my partition, I'm going straight down and say, well, what's the value that's right in the middle? What's the y value that's right in the middle? And those y values that are right in the middle, those are the ones that I want. So I want 7. I want 4. I want 10. So a midpoint sum, I need to have an even number of partitions. So that way I can create a middle. I mean, I don't have to have even number of midpoint partitions. I just need to have an even number of regular partitions so I can create a midpoint. And then I need it to be normed width. So therefore, if I wanted to do a midpoint sum, my base was 8 of my first partition, and my first height would have been 7. I don't take the 2, which is the left. I don't take the 6, which is right. I take the 7, which was in the middle. That's a midpoint sum. Then I have 8 times 4 and 8 times 10. That is a midpoint sum. All right, let's try one more, friends. One more. Say I give you something like this. We're going to go from 1 to 9. And let's do negative x squared plus 10x. And we're going to say let there be 8 partitions. So if we the first thing we have to do is we have to figure out how we're going to count. So I'm going to figure out what I'm going to do, or using this, I'm sorry, let me backtrack 1 second here. We're going to figure out the left sum, the right sum, trapezoidal sum, and the midpoint sum. So knowing that I'm going to eventually use a midpoint sum, I need to go ahead and make this normed width. So in order to make it normed width, I'm going to have to go delta x. So figure out, and by doing this, it's going to allow me to also know what I'm going to count by. I'm going to take my a value, my b value, which is 9 minus 1. So there's a 9 minus 1. I'm subtracting the bounds, and I'm going to divide by the 8. Let me just put this up here again so you guys know, beyond a shadow of a doubt, where all the numbers are coming from. So 9 minus 1 over 8. So if I use an approximate for this, notice I have 8 over 8. This says I'm going to count by ones. So I'm going to start at 1, and I'm going to count by ones until I get to 9. So let's go ahead and create then our table that we're going to use here. So we have x, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we got to plug these values in to see what they're going to be. So that'd be 9. It's going to be 16. I plug 3 in there, I'm going to get 21. I plug 4 in there, I'm going to get 24. I plug 5 in there, I'm going to get 25. 6 in there, 60 minus 3, that'd be 24. Oh, it is a parabola, friends. That was always making life just a little bit nicer on us. So if I keep going here, plug 7 in there, that'd be 21, 16, and 9. All right, let's go ahead and finish off our little. So we create our table. And again, all these, the 9, the 16, 21, 24, that just came from putting all the x values into my function and figuring it out there. So just take all your x values, take all the x values, so literally right up here, and plug them into your function. Because this right here is representative of f of x. Okay. Why don't you guys go ahead and pause the video now and see if you guys can go ahead and do a left sum, right sum, trapezoidal sum, and a midpoint sum. Go for it. All right, here we go. Let's see how you did. 1. Again, it's normed width, so we've already created all these to be 1, which is what we said we were going to have to begin with. So if I want my left sum, the left sum is going to be doing all the left values. So that would be these ones: left, 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 left. So the left sum is going to be approximately, since I know they're all going to be the same, we could probably just shortcut this. I'm going to just type it out. 1 times 9 plus 1 times 16 plus 1 times 21 plus 1 times 24 plus 1 times 25 plus 1 times 24 plus 1 times 621 and plus 1 times 16. Did we get our 8 partitions? 1, 2, 3, 4, 5, 6, 7, 8. We did. All right, the right sums, those are going to be using all the numbers going down the right side. All right, so we have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, again, you can plug all these into your calculator. So the green would be 1 times 16 plus 1 times 21 plus 1 times 24 plus 1 times 25 plus 1 times 24 plus 1 times 21 plus 1 times 16 plus 1 times 9 equals 1, 2, 3, 4, 5, 6, 7, 8. All right. The trapezoidal sum, remember, that's going to be all of them together. So this is going to be about 1 times 9 plus 16. I can't believe I got to do all 8 of these here. 1 times 16 plus 21. 1 times 21 plus 24. Plus 1 times 24 plus 25. Plus 25 plus 24. I'm going to run out of room. Please don't run out of room. One times 24 plus 21. I can hear you. You should have just done the left sum plus the right sum. Yeah, I probably should have. 1 times 21 plus 16. Oh, I might actually make it. Got it right sloppy, but it looks like I will barely make it. 16 plus 9 divided by 2. 1, 2, 3, 4, 5, 6, 7, 8. There we go. All right, now I got the midpoint sum. Now remember, on the midpoint sum, I got to skip. So I'm going to go from 1 to 3. So now that width is 4. Oh, 2, I lied. I'm going 3 to 5. 5 to 7. I have 8 partitions, so I can pull this off. 2. And for this one, it's going to be the number in the middle. So my midpoint sum is going to be 2 times 16 plus 2 times 24 plus 2 times 24 again plus 2 times 16. And that gives us a different type of approximate as I use the numbers that were actually in the middle of those larger partitions. And again, if you notice, midpoint sum always has half the number of partitions as the left, right, and trapezoidal. All right, friends, that takes care of it. Hope you have a wonderful, wonderful afternoon, and I will see you guys in the morning. Take care.